In this today lecture, we go to see some solved examples in transient response of the circuit using Laplace transform. So consider the problem. In a series LC circuit, the supply voltage being V equal to Vm into cos t. Find I of t with zero initial conditions. Assume L equal to 1 Henry and C equal to 1 Farad. So that means it is a series LC circuit. So consider, so yes, only LC is present. Okay, so this is the LC circuit. C and L, the value of C is 1 Farad and L is 1 Henry. Assume all the initial conditions are 0. Apply KVL for this corresponding loop. So therefore I of S into SL plus 1 by CS, which is equal to Vm is constant. For the cos t, the Laplace transform is S into S divided by S square plus 1. Okay, so now this term is taken to the RHS. Okay, so it should be like this. So if we rearrange these equations, finally we get, which is equal to Vm into S square divided by S square plus 1 the whole square. Okay, so now apply partial fraction method in order to get the values. Okay, so I split the equation, looks like this: S plus j into S minus j into S plus j into S minus j. So this equation is rearranged like this. If I take the partial fraction for this, it should looks like this: Vm into k1 divided by S minus j square plus k1 conjugate divided by S plus j the whole square plus k2 divided by S minus j plus k2 conjugate divided by S plus j. If I want to find the value of k1, then I substitute S is equal to j. Okay, so if you substitute S is equal to j, means this two term will cancel, k1 and k2, and this two term will present. So here if substitute j, it should be equal to j plus j, which is equal to 2j the whole square. Similarly here also 2j the whole square, sorry. Okay, so if you simplify this, you got the value of 1 by 4. Similarly, in order to find the value of k2, this is the generalized formula: 1 divided by n minus 1 factorial into d by ds into s minus some a the whole power n into I of s. So here n is equal to 2. So substitute the values and do the simplifications. So this is the final expression, and the final value of k2, which is equal to minus j by 4. So to find the value of k1 dash and k2 dash, just simply take the complex conjugate of k1 and k2. Here there is no imaginary term is present, so that k1 dash, which is equal to 1 by 4. For k2 dash, here minus j by 4 is present. If I take the complex conjugate, which results j by 4. So therefore k1 dash and k2 dash values are looks like this. If you substitute the value of k1 dash, k2 and k2 dash in the above equation of I of s, now you take the inverse Laplace transform. Okay, so we know that this term is replaced by t into e power jt. This is replaced by t into e power minus jt. Okay, similarly take j outside and it is replaced by e power jt plus e power minus jt. Okay, so this is the term. Now I rearrange these equations. So we know that take j outside. Okay, put negative sign is there. So if I rearrange this equation, it leads to sin t, and similarly take t outside, which is equal to cos t. Okay, so from this equation I rewrite this. So this is the final expression for the corresponding problem. Okay, so then now I move on to the next problem. So in this problem, find the value of v naught of t for time t greater than 0. So this is the circuit. Initially the switch is closed. When time t equal to 0, then only my switch is open. So at that time, what is the value of v naught of t? V naught of t is nothing but the voltage across the RL combination. Okay, so now consider for the initial condition, when time t less than 0, the switch is initially closed. The corresponding circuit looks like this. The initial voltage across the capacitor, which is equal to 0, because the capacitor is bypassed by a short circuit. The short circuit voltage across the capacitor, which is equal to 0. So the initial current through the inductor, which is equal to 70 divided by 350, which gives around 0.2 ampere. Okay, so these are the initial conditions. Now the switch is open, the circuit looks like this. Now you apply the loop equation for the corresponding circuit. Okay, so this is the value of IFS for the corresponding circuit. Directly you write the loop equation. This is a single loop, so that the total voltage, which is equal to 70 divided by S plus 0.04 divided by 350 plus 0.2 S plus 1 divided by S into 512 into N. N is nothing but nanofarad, so only I put N here. Directly write the equations. Okay, so therefore here I need to find the value of V of S. So to find the value of V of S, just you should multiply the value of I of S with these values. Okay, so you add these two values and multiply by the current and less the corresponding value with the initial voltage. So this is the equations. Now you substitute the value of I of S. Okay, and do the simplifications. That means you put the value of N and you do the simplifications. So this is the final expression. So it is a quadratic equation. You should find the roots. So for this quadratic equation, I rewrite this equation like this: S plus 875 minus J 3000 into S plus 875 plus J 3000. Use the calculator in order to find the roots, or otherwise use the formula minus b plus or minus square root of b square minus 4ac divided by 2a. So use any one of the methods to find out the roots. Okay, now you should find the values using partial fraction method. It should be k1 divided by s plus 875 minus j 3000 plus k2 divided by s plus 875 plus j 3000. So to find the value of k1, you substitute s is equal to minus 875 plus j 3000, and finally you get the value of around 65.1 at an angle of 57.48 degree. Just doing the simple mathematics. Okay, so similarly to find the value of k2, you substitute s is equal to minus 875 minus j 3000 and you do the simplifications, which leads to the value of 65.1 at an angle of minus 57.48. Now you substitute these two values of k1 and k2 in the above equation, v naught of s, and the resultant equation looks like this. Okay, now we have some general Laplace transform, which is says functional transforms. So whenever our function looks like in the format, the final inverse Laplace transform of this format, which leads to f of t equal to 2 into the value of k into e power minus at into cos of bt plus theta. This is the final expression. Just you remember this formula. So in this equation is similar to this equation. So here k is equal to 65.1 and theta is equal to 57.48. Okay, here a is equal to around 875 and b is equal to 3000. So substitute these values. So the final value of v of t, which is equal to this thing. Otherwise you go for the normal expansion method. So it is very simple. Just you remember this formula, you rewrite the equation directly. Okay, so this is the final expression. So similarly, so this is the final expression, which is v naught of t, which is equal to 130.2 into e power minus 875 into t into cos of 3000 t plus 57.48 degree. Okay, so whenever we perform some partial fraction expansion, so there is some direct formula will be there. Suppose you take for example, this is your final format. Whenever you're taking the Laplace transform, just you convert this function into time domain as directly as like this. So which is nothing but 2 into k1 into cos of omega t plus at an angle of k1. What is the value of angle? You should substitute here. Similarly, here we see in the problem. Suppose if it is in the format, then just rewrite the equation. I'm already told that. So it is replaced by 2 into the magnitude k into e power minus alpha t into cos of beta t plus the angle of k2. You substitute the value directly. And also we see some direct substitutions in the Laplace domain. So if it is a series circuit, if I want to find the value of V1 or V2, just apply the voltage division technique what we used in the DC circuits. It is very simple, but we take Laplace transform here. That is the difference. Otherwise, the concept is same. Okay, just use the voltage division technique in order to find the value of V2 or V1, whatever it is. Similarly, in order to find the value of Z equivalent, just simply add Z1 and Z2. Okay, so this is the corresponding formula. It is similar to the voltage division technique. So there we use only the resistance values and some DC input voltage values. Here we take some Laplace transform and just we apply the same technique. So similarly, if the current division technique is present, if the current division technique is present also, similarly, so where they were use current division technique, so similarly here also we use the same formula, and you should find the value of I1 of s and I2 of s. Okay, so here you just remember, you need not to, you should remember there is no mistakes whenever you transform into the Laplace domain. Okay, it is very important. If you do mistakes in converting this time domain equation into the frequency domain or s domain, just you need to be careful. Okay, otherwise the final answer should be the same. And similarly, whatever the theorems we used, it is also applicable in the Laplace domain also. We use the nodal analysis also and mesh current analysis, so all are same. Okay, what they used in the DC circuits. And if the mesh analysis is possible only if the circuit is a planar circuits. If it is a non-planar, it is not applicable in the S domain. Okay, so these are some procedures to apply the nodal voltage equation. The first thing is transform the circuit into the S domain using current sources to represent the capacitor and inductor with initial conditions. Suppose if it is a mesh analysis, then you represent the capacitor and inductor with the corresponding voltage sources. That's all. If it has any initial values. And similarly, select a reference node for the node analysis and identify a node voltage at each of the non-reference nodes and a current with every element in the circuit. Okay, so in the next thing, write KCL connection constraints in terms of the elements currents as the non-reference nodes, and use the element admittances and the fundamental properties of node voltage to express the element currents in terms of the node voltages. And the last thing, to substitute the device constraints, okay, from step 3 into the KCL connection constraints from step 2 and arrange the resulting equations in a standard form. So this step we use in the previous lectures. So use Cramper rule, just you need to solve the equation. So that is the procedure they follow. So in the previous lectures we solved some problems. The steps are elaborated given here. That is the thing. Okay, I hope you have very clear about the transient analysis of a circuit using Laplace transform through the entire lecture. If you have any queries or doubts, put your comments on the comment section. Thank you.